Okay, I'm going to talk about Wilson's theorem. Um, and this is very similar in flavour to Fermat's theorem. Anyway, let me state it. If P is prime, then P minus 1 factorial equals minus 1 modulo P. That's it. But it's very, very useful. It crops up over and over again. I think this is one of the theorems that you can assume in Olympiad questions. But I'm going to prove it anyway. P minus 1 factorial, this is a proof. P minus 1 factorial equals 1 times 2 times 3 times 4 times 5 times P minus 2 times P minus 1. And then I'm going to make the observation that this is equal to 1. This one here is equal to minus 1. Everything here being modulo P. So what have we got left? We've got an even number left. And I'm going to make use of the fact that modulo P, for any A, we have got there exists a B not equal to A with AB equals 1. So for example, if P equals 13 and A equals 3, then B will equal 9 because AB, which equals 3 times 9, which equals 27, equals 1 modulo 13. I'm not proving. I'm not going to prove that, but it's kind of obvious when you think about it. So if we take our factorial, our P minus 1 factorial here, well, what it is, it's 1 times some stuff times minus 1 for the P minus 1 right at the end. And all of these terms here, 2 times 3 times 4, all the way up to P minus 2, there's an even number, and they all cancel in pairs. I'm going to use a slightly different colour here. So this one might cancel out with that one, this term here might cancel that, 2 and 3 might cancel out, this one and this one might cancel out, all equal to 1. Go back to black. So P minus 1 factorial equals 1 times 1 times 1 times 1 times 1 times minus 1 minus 1. Everything being modulo P. So for example, if I say P equals 7, then I'm asserting that 6 factorial equals minus 1 modulo 7. Well, 6 factorial equals 720, so we better work out what that is modulo 7. Well, 720 equals 20 modulo 7 equals 21 minus 1 equals 0 minus 1 equals minus 1, everything being modulo 7. So there's the theorem in that case there. Let's take P equals 13 as a second example. Then we've got 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12. And now what I'm going to do is I'm going to explicitly cancel these guys out, because I know that 2, well, the 1's on its own, isn't it? So we'll leave these 2 here. That's just your minus 1 at the end. 2 times what equals 1 modulo 13? Well, 2 times 7 is 14, which equals 1. What about 3? 3 times 9, because 3 9's 27, which is 26 plus 1, which is 1, check. 4 times what? It's 4 times 10 equals 40, which equals 39 plus 1 equals 1, check. What's next? 5 times 8, 40 as well, yeah, equals 1, check. And what have we got left? 6 times, well, there's only one number left, 11, equals 66, equals 65 plus 1 equals 1. Everything being modulo 13. So if we look at these numbers here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just need to write them out in a peculiar order. 1 times 2 times 7 times 3 times 9. See, I'm just reading them off here. This one's 4 times 10, 4 and 10. Done that one 5 times 8. That's that one and that one. And there's 6 times 11 times 6 times 11. There's the 11. Where's the 6? There it is. Times 12. All I've done is shuffle these guys around. The 3's gone there. The 4's there. 5 is there. 6 is there. 7, where's that? There. 8 is there. 9 is there. 10's there. 11's there. 12's there. And of course, by bracketing it, dong, 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 we get 12, which equals minus 1 modulo 13. Job done. Okay, I'm going to stop there. That is Wilson's theorem. If P is prime, P minus 1 factorial equals minus 1 modulo P. Okay, I'm going to stop there.